This lesson is going to go through analyzing dimensions. So when we make changes to a figure, if we enlarge something or reduce something, what do we see happen to the side lengths? But then we want to be able to understand kind of immediately without having to do a bunch of calculations. How does that affect the change in the area and the change in the volume? So you guys did an investigation on Desmos, and then hopefully it at least gave you a basic understanding. And the idea of what we should have seen was about ratios. So these aren't actual numbers. So let's say that you had some figure. Let's make it a box. And then you made your box larger. But you kept them similar, meaning when you enlarged it, you like doubled everything. Things kind of grew the same way. So like if this had been a 3, now this is a 6, etc. So what you guys determined then is that the box grew from having side lengths of 3 to side lengths of 6, and that ratio reduces to a 1:2 ratio. Okay. So this was called the scale factor in your investigation. This has to do with, and I'm going to use a couple of vocabulary words so you know when you're answering what, dimensions or side lengths. So when you hear scale, dimension, or side lengths, those are all just talking about the measurements marked on the drawing. Okay? And so what you guys have is you have here actual side lengths went from 3 to 6 when you enlarged the figure. What that means for us is that we could also have the reduced ratio of the side lengths is 1:2. And that's the old one compared to the new one. Then we want to talk about area. Now, I didn't give you all of the values for these figures, so you can't calculate area of one side or the entire surface area, but based on our investigation, we saw a pattern. If you know that the side lengths doubled, they went from 3 to 6, they have this ratio of 1:2. You don't know the actual areas of these figures, but you do know how much the area grew. According to our investigation, this means that the old area compared to the new area would be a ratio of 1:4, meaning the new area would be 4 times larger than this one. So any area calculation on this large shape, I would expect to be 4 times larger than the same area calculation on the small shape. Then we talked about volume. Again, I haven't given you enough values on these shapes for you to calculate the volume for me, but knowing this key piece of information, this scale factor or this ratio of the sides, tells me that if the sides grew double, the volume would grow 8 times larger. That means I expect the volume of this large box to be 8 times whatever the volume of this small box is. I don't know the actual numbers, but that's what I expect. So why do I expect that? It's because of what I saw in the investigation. So in the investigation, again, we used actual examples to see patterns, but here I'm just summarizing the patterns, and the patterns are ratios. They're not actual numbers, but they relate the side ratio to the area ratio and to the volume ratio. And we call that side ratio scale factor sometimes, or dimensions. So don't lose track of that. And then we have an old compared to a new. And what we said is if you knew an old side length and a new side length, and you can put those 2 dots between them to make the ratio, you don't know the areas. Like in my picture that I had over here, you don't know the areas, but based on our investigation and the patterns we saw, we know that the area ratio will be like the square of that side length ratio compared to the square of the new version. And the volume would be the cubes in those relationships. So these would be the different relationships between them. Notice the area is based on the scale and the volume is based on the scale. It kind of all comes back to the scale. So I'm going to use that ratio chart to help me solve the problems that ask about these changes for these different dimensions. So read the problem carefully. They say if the dimensions, so remember the dimensions are related to side length or scale of an object are doubled. So here's what they told me. Actual, nothing so far. But ratios, I have, I'm going to fill in what I have. Do I have sides? Do I have areas? Do I have volumes? How are they related to each other? So I'm going to use this kind of like chart just to organize my information. So when they tell me the dimensions are doubled, that means I don't know what the original side lengths are, but I know if this one was a 1, then this one was a 2. Whatever the original side lengths were, when you reduce it down, it's 1 to 2 is the ratio for doubling. Then it asks me, what is the ratio of the surface area of the original to the enlarged object? So when they ask about surface area, that is an area calculation. So it's going to be related to the area information in our chart. Remember what we said. In our chart above where we generalize things, we said if you knew the scale, the area is related to that by the squares of those numbers. That should be a B. So if I know that the sides are related by a ratio of 1 to 2, then I basically know that A is like a 1 and B is like a 2. So in my area ratio, my A squared is like 1 squared and my B squared is like 2 squared. So that turns out to be 1 to 4. Okay, that's the ratio. That answers the question because they just asked me for the ratio. So I would say the ratio of the surface areas is 1 to 4. So that's one answer to this question. The next portion asked me about the ratio of the volumes. So again, remember the relationship here, it really has nothing to do with the areas, but if you knew that this side length ratio, the volumes are the cubes of those numbers. So if you already know that A is like a 1 and B is like a 2 in the ratio, then you can find the volume ratios by cubing A and by cubing B. So 1 cubed is 1 and 2 cubed is 2 times 2 times 2, which is 8. So we have our volume ratio of 1 to 8. So the volume ratio is 1 to 8. So again, how did I figure that out? I isolated the information they gave me and filled it into the ratio chart, and I had to have this idea memorized, the idea of how they're related to each other. All right, so then in part B, it says, what factor did the dimensions get multiplied by? So this doesn't ask for a ratio, this asks for a factor. That kind of question is basically saying, sorry about that. That kind of question is basically saying you had an old number, it got times by some factor, and that made a new number. But your ratio helps you figure this out. This is the same in the ratio because they reduced. So your old in your ratio is like having a value of 1, even though that might not be the actual number, and your new is a 2, and your factor is what you're trying to figure out here. So 1 times what makes 2, or you can think about this as dividing both sides by 1, and you're getting a factor of 2. So the dimensions were multiplied by a factor of 2. Then it asks the same question for the surface area and for the volume. The surface area was multiplied by a factor of, and take a look at that ratio. It changed from a 1 to a 4 in our area. So it's the same idea, except for now we would be changing from a 1 to a 4. So if I divide both sides by 1 there, I get that x is 4, so surface area was multiplied by a factor of 4. And now I'm going to do the volume. So volume was multiplied by a factor of, and you don't have to do all this work when it's 1 as the beginning of the ratio. It's clearly a little bit easier than if the number was different. Then I would get a factor of 8. I'm just trying to point out to you guys the different ways you answer the question. If they're asking you for a ratio like they were in part A, then the answer is like this. If they're asking you for what factor things got multiplied by, they don't want the whole ratio. They want to know how you change it. Like, how do you get from the old to the new? What is it multiplied by? And then lastly, it says if the original surface area of the object was 28 centimeters squared, what is the new surface area of the object? So now they're giving me actual measurements. And so I know that I want to compare the old to the new. And this problem is talking about, I should say surface area. So the original surface area was 28. And the question is, what is the new surface area? This problem by itself would mean nothing, but we have this chart of ratios and we have this information right here about area, that the ratio was 1 to 4. So we know that the ratio, the way that this is supposed to work out, is that the old should be 1 compared to 4 times that for the new. And you can actually set up a proportion with each of these. 28 is the old compared to an unknown new. That should end up equaling the 1 to the 4 ratio. And you can solve this by cross multiplication. So 1 times x is x, and 28 times 4 is 112. And so x would be equal to 112. That means the new surface area of the object would be 112 centimeters squared. And then we're going to look at part D. It just asks a slightly different question. If the enlarged or the new volume of the object was 136, what is the original volume of the object? So this time, notice the problem's about volume, and they're giving you actual numbers, not just ratios. And so we're talking about comparing old to new. And in this case, they want to know the old or the original, and they're telling me the new was 136. The only other piece of information I know is my ratio. So look back at the original problems info, and we have a volume ratio here, and it was 1 to 8. So when I'm looking at the ratio reduced, the old should be 1 compared to a new of 8. And again, these transform into a proportion. How does an original compare to 136? It should be the same as this ratio I know that I'm supposed to get of 1 to 8. So then to solve this, I'm going to cross multiply. 8 times x is 8x. 1 times 136 is 136. And then I'm going to go ahead and I'm going to divide both sides by 8. And again, you guys can use a calculator in our course for almost everything. So 136 divided by 8 gives me 17. So my original volume, if this was the case, would have been 17 centimeters cubed. All right, so we're going to go through this one more time, the couple of examples. If the volume of an object was multiplied by 5, what is the ratio of the surface area? So they're telling you volume and they're telling you multiplied by 5. So what they're giving us is a ratio, but they're not giving us the side length ratio. They are giving us the volume ratio. So the volume got multiplied by 5 would mean that I have a 1 to 5 ratio for my volume. So then the first question here is, what is the ratio of the surface area? And then the ratio of the dimensions. So again, I'm answering questions about ratio, so this chart should do it, but I have to know the relationships. So my side length ratio is related to my area, and my side length ratio is related to my volume. So this right here is where we're going to get most of our information. Basically, we're saying our 1 to 5 ratio is basically telling us our a cubed is like a 1 in this problem, and our b cubed is like a 5. I'm going to cube root each of these to see what a and b values I have. So the cube root of 1 is 1. The cube root of 5, I don't know, and I'm just going to write it as the cube root of 5. That's fine. So those are my a's and my b's. Now I can go and I can fill those into the chart. This side length or scale ratio of a to b, I now know is 1 to cube root of 5. And you might not like cube root of 5, but remember, it's just like 1 point something. Who knows? And then my area ratios are a squared and b squared. So if you know that a is 1, then a squared is still 1. If you know that b is the cube root of 5, then b squared is the cube root of 5 times the cube root of 5, which is the cube root of 25. So we can just write that there. And this gives you all of your ratios. So our surface area ratio is 1 to the cube root of 25. And our dimension ratio, remember dimensions is the same as side lengths or scale. So our dimension ratio is 1 to the cube root of 5. All right, what factor did the dimensions get multiplied by? So remember this whole idea of if they ask you factor, you have an old, which for our factors, we're looking at scale for dimensions. It was 1 was multiplied by some factor to give us the cube root of 5. So the factors, what I'm looking for are my variables. So 1 times what equals the cube root of 5, and I get the cube root of 5. So the dimensions by a factor of cube root of 5, and you can repeat that process. Pause the video if you want to check it here. Sorry, not dimensions. You can repeat that process. You can pause the video if you want to. Here, the area by a factor of the cube root of 25, and the volume by a factor of 5. All right, the next one says if the original surface area of the object is 50 centimeters squared, what's the new surface area? So they are giving you some actual measurements. Remember, you want to divide them up old to new. So they're telling you the original or the old was 50, and your job is to find the new. And then you want to look back at your ratio chart and see what ratio you're dealing with. This was specifically for area, and the ratio there was 1 to the cube root of 25. So then our proportion is going to say 50 gets turned into x, just like 1 gets turned into the cube root of 25. And we can cross multiply to solve this. So 50 times the cube root of 25 is just going to be written as 50 cube root of 25. And 1 times x is x. And that is our answer. X is 50 cube root of 25. So 50 cube root of 25, and it was area. So it would be centimeters squared. Same idea with part D. So that they said if the enlarged or new length of the object was 12 centimeters. So they're giving us an actual measurement. We want to compare the old or the new. This time they gave us the new, and they asked us for the original. Now, this was about length. Length is a dimension or a side length or part of the scale. So when you go back to your ratio, you want to look specifically at the scale or the side length ratio. And for this problem, that was 1 to cube root of 5. And so this means x gets turned into 12, like 1 gets turned into cube root of 5. And we're going to go ahead and cross multiply to solve this. So x times the cube root of 5 equals 12 times 1, which is 12, and divide by the cube root of 5. And I'm going to actually, for our purposes here in this problem, I'm going to let you guys keep it as 12 cube root of 5, and then this was centimeters, 12 divided by cube root of 5, or you guys can put it all into the calculator and you can get the decimal approximation for that. So hopefully this helps you with those analysis problems.